Hey everyone, welcome to module 7.2.3, which is our continuation of electrophysiology, and we're getting into graded potentials here. Um, so we can highlight graded potentials by starting off with changes in the transmembrane potential. And remember, the transmembrane potential rises or falls in response to temporary changes in membrane permeability, which results from the opening or closing of specific membrane channels. Remember, membrane permeability to sodium and potassium determines the transmembrane potential, and that sodium and potassium channels are either passive or active. Membrane channels also allow for that ion movement, and each channel is specific to one ion type, either passive channels, which can also be called leaky channels, or active channels, which have further subcategories of chemically regulated or ligand gated channels, voltage regulated channels, or mechanically regulated channels. So remember from the previous modules that passive channels or leaky channels help to maintain the resting potential. They're always open and free flowing, and they help to set that potential at minus 70 millivolts. When speaking on the three active channels, so a chemically gated or a ligand gated channel is a sodium channel that opens in response to the presence of ACH or a ligand binding at that site. You have a voltage gated sodium channel that responds to changes in the membrane potential, and at its resting membrane potential of minus 70 millivolts, the channel is closed, and at minus 60 millivolts, the channel opens, and at positive 30 millivolts, the channel is inactivated. And then a mechanically gated channel, which opens in response to distortion of the membrane. The next couple slides just highlight what we said a little bit more. So the chemically gated or the ligand gated channels open in response to chemical bonding and are located on the cell membrane. The voltage open in response to a shift in the transmembrane potential. And then mechanically regulated channels open in response to membrane distortion. So when channels open, ions flow along the electrochemical gradient, and those are by a couple forces, either diffusion, which it goes from a high concentration to a low concentration, or from electrical attraction or repulsion. This is just a graphic of the sodium potassium pump, which we'll get into a little bit more here. So we can compare a cell to a leaky fishing boat. It's kind of loaded with tiny fish floating in the sea, and use it as kind of comparison between the sodium potassium pumps. So the whole kind of represents the plasma membrane. The fish represents plasma. Potassium, and the ocean water represents sodium. And as the boat kind of rolls along, the water comes in through the cracks, and the fish kind of swim out of those cracks. So if the boat is to stay afloat and upright, and we're able to keep the fish, we have to pump the water out and then recapture the lost fish. And similarly, at the normal resting potential, the cell must bail out sodium ions that leak in and recapture the potassium ions that leak out. And the bailing out takes place through the activity of an exchange pump that's powered by ATP. The ion pump involved is the carrier protein sodium potassium ATPase. And this pump allows the exchange of 3 intercellular sodium ions for 2 extracellular potassium ions. And at the normal resting membrane potential, this pump ejects the sodium ions as quickly as they enter the cell. And in this way, the activity exchange pump exactly balances the passive forces of diffusion, and the resting membrane potential remains stable because the ionic concentration gradients are maintained. This just highlights an overview of what we just talked about there. Then we're we're getting the graded potentials here. And graded potentials, or the resting state, is the opening the sodium channel produces a current, which causes that graded potential. So remember that graded potentials or local potentials are changes in the membrane potential that cannot spread far from the site of stimulation. And any stimulus that opens a gated channel kind of produces that graded potential. And integrated potential, the degree of depolarization decreases with the distance away from the stimulation site. Well, why? Depolarization lessens with the distance because the cytosol offers considerable resistance to ion movement, and because of some of the sodium ions entering the cell then move back across the membrane through those sodium leak channels. At some distance from the entry point, the effects of the membrane potential are undetectable, but the maximum change in the membrane potential is proportional to the size of the stimulus, which determines the number of open sodium channels. And the more open the channels, the more sodium ions enter the cell, the greater the membrane area is affected, and the greater the degree of depolarization. And when a chemical stimulus is removed from the normal membrane permeability is restored, the membrane potential soon returns to that resting level. And the process of restoring the normal resting membrane potential after depolarization is called repolarization. Repolarization typically involves a combination of ion movements through the membrane channels and the activities of ion pumps, especially the sodium potassium exchange pump. So, what happens to the membrane potential when a gated potassium channel opens? So, opening the gated potassium channel has the opposite effect from opening the gated sodium channel. The rate of the potassium ion outflow increases, and the interior of the cell loses that positive ions. So, in other words, the inside of the cell becomes more negative. The loss of those positive ions produces what we call hyperpolarization, or an increase in the negativity of the resting membrane potential. For example, from minus 70 millivolts to minus 80 millivolts or more. And again, a local current distributes to the effect of the adjacent proportion of the plasma membrane, and the effect decreases with the distance from the open channel or channels. So graded potentials occur in the membranes of many types of cell, not just in nerves and muscle cells, but epithelial cells, gland cells, adipocytes, and a variety of sensory receptors. Graded potentials often trigger specific cell functions. For example, graded potential at the cell surface of a gland cell may trigger the exocytosis of secretory vesicles. And similarly, at a neuromuscular junction, the graded depolarization of the motor end plate by ACH triggers an axe potential in the adjacent proportions of the sarcolemma. The motor end plate supports the graded potential, but the rest of the sarcolemma consists of excitable membranes. And these areas of membranes are different because they have voltage gated channels. So in step one, sodium ions enter the cell and are attracted to the negative charges along the inner surface of the membrane. And as these additional positive charges spread out, the membrane potential shifts towards 0 millivolts. Any shift from the resting membrane potential towards a more positive potential is called a depolarization. Note that this term applies to changes in the potential form, as well as the membrane potentials that are above 0 millivolts. In all these changes, the membrane potential becomes more positive. In step two, as the plasma membrane depolarizes, sodium ions are released from their outer surface, and these ions, along with the extracellular sodium ions, then move towards the open channels, which replacing the ions that have already entered the cell. This movement of positive charges parallel to the inner and outer surfaces of the membrane is called a local current.